Hello. So today I wanted to show you a little bit about what I've been doing in the lab involving 3D printing a glass. So I'd like to show you how I made the glass, how I print with the glass, debind it, and then finally sinter it so that you can get a bowl or a head or some other figurine like that in pure glass. So this is not mixed with plastic. This is 100% glass. So let's get right to it. So the first thing you got to do is you got to actually make the stuff. So actually, how I've been doing that is I started at the virtual foundry. So it's the same place that makes the filament that has copper in it or has steel in it. So it's a little company in Stoughton, Wisconsin. They're really wonderful people. It's a great town too. And I went and I visited them, and while I was there, we made a new filament that was just mixed with small particles of glass. So this is it's being compounded through this machine, and it's just being squirted out. And all it is it's just plastic, so PLA, mixed with loose glass. And the loose glass might look like this if it was in a jar, or if you look at it under a microscope, it might look like this. So they're about 100 microns in size or so, and they're literally just small Pyrex glass beads, and then it's about 70% of the plastic weight. And so here's like a little string of filament, and it's, again, just like regular 3D printer filament. Here I am being very happy. I had made my first roll, so I did the compounding and the extruding and the winding and the shrink wrapping, which was the hardest part. There I am in their workshop. And so you get this roll of plastic, and then you can 3D print with it. And you 3D print with it very similar to regular plastic. So here is, it just being printed. It's coming out of the nozzle. And so some considerations are you need a hardened steel nozzle, so no brass. It's very extremely abrasive. It's like sandpaper. Even steel might not be enough. And then they recommend a 0.6 or a 0.8 millimeter nozzle. As usual, I am flirting that rule, and I am using a 0.4 millimeter nozzle. And this is just on my Creator Pro. I'm printing some dog bones. And the filament is actually less difficult than, for instance, the steel filament. Not as easy as the copper, but it's not that bad. It's very flexible, so that's not really a problem. What is a problem is jamming. And so actually, this is counterintuitive, but if you're getting jams, it can be helpful to actually lower your nozzle temperature. So that's something I found out, is that when you lower the nozzle temperature, I think it results in the parts, it results in the glass not separating from the plastic. So when it gets too hot of a temperature, it separates from the plastic. All right, so let me just look for a couple of green parts. So here are some green parts I printed. So this is what comes out of the printer, okay? So this is, 20 to 30% plastic by weight. And, it prints very much like regular PLA. It actually prints pretty good. You can get, pretty fine detail. So there's my head, a standard cube, and some dog bones. And I ended up printing much larger dog bones. These are for tensile testing. And let's see. So those are some green parts. And here are some more green parts. These are little plugs I made. You'll see why. They're meant to go in a funnel. And yeah, so those are some green parts. Here's another green part. So this is a glass one compared to copper. So this is, again, still mixed with plastic. And to show you how this behaves, this was printed in vase mode, so 0.6 millimeters thick. I used extra extrusion. And there it is. And I think I had a video. And here we have a green part. And so there's some copper. So I already did copper. We all know about copper. And then this is just showing you that it is, it's flexible. It's got plastic in it. Nice and shiny on the bottom. But yeah, this is a flexible part. So not at all like regular glass. All right. So now that we have that, it's mixed with plastic, right? So we have to debind the part. And so I did a little experiment, as I do whenever I have a new filament, where I heated it up. So this is actually in the process of being heated up. And you can see it turns black instead of being nice and white or gray on the bottom where the heat source is. And then as you heat it up more, it reveals the glass beads that are inside. And this is kind of surprising. I was expecting it to hold its shape, but it literally is like a bag of glass beads once it's been debound. And then this is what you get. You get these little beads of glass. You get these little beads of glass. And that's what you get. So the first time I tried sintering this, I tried it at 700 Celsius as my peak temperature. Put it in the oven. I took it out. I poured off all of my refractory material. And I'm going to pull out a part, and you'll see the problem with it. This is at 700 Celsius.
Something survived. Is it fragile?
I'll let myself talk.
Yes, it's very fragile.
So that's my cube.
But, so this looks to be glass that hasn't been, you see it's flaking off in my hand. Alright. Let's save that.
So there is a cube, it just crumbled into absolutely nothing.
Alright.
And you're left with this glass, which honestly you could probably, save for some kind of project maybe involving loose glass. It's, kind of cool. But that's obviously not what you want. So that's at a peak temperature of 700 Celsius. And so I tried 700, 800, 900, 1000, 1100, 1200, and 1300. And basically what I found was that anything above 800 or so would solidify the glass enough to hold together. And so here is, I'm having trouble. Let's try one more time. And so here is a piece of glass that has been held together by sintering. And so you can actually see you've got mostly round grains that are stuck together, and you've got a solid glass part. And let's take a look at a couple of those. So here is a sintered versus a green head. So as usually I use my heads as source material, as kind of standard models, even though the model is kind of messed up. It's like hollow on one side, so it squishes. But yeah, it absolutely works. I have one right here. There it is. Not really great on the webcam, but it is a solid, pure glass head. Not quite solid. And you can see that it's white. And the whiteness is actually mostly due to the porosity of the part. So it has air trapped in it. It scatters light, and so it's not really transparent. Here's a cube. So there is a glass cube, sintered and green. And we can see that it actually does quite isotropically shrink. Even this little kind of booger of filament that got left behind is there. So it really captures the detail quite well. And it does shrink, which I wasn't really expecting. From my understanding of sintering, it requires like a vapor phase or a liquid phase. And this actually wasn't hot enough to melt the glass. It was just hot enough to soften it. So I was kind of surprised to see that it shrank, but it does isotropically shrink. So now I want to do some experiments. So one of the first things I tried actually was I wanted to use the porosity to my advantage. So you might have seen this video already on my channel a few weeks ago called Science Coffee. But what I did was I printed basically these cone-shaped parts. This is them printed. And then I placed them in a funnel, I'm kind of wondering why I don't have that picture here. Here's one actually. And then I placed them, I kind of smushed them into this funnel so that it would be a very tight fit. And then I tried to use it to make coffee. So here's one setup where I have, my coffee and I got my funnel, my water. This actually did not work very well. And I ended up having to use suction. So here it is on this Hackaday page. So they wrote this up. That was nice.
It in your mouth.
I'm not going to show the whole video, but there's the part. There it is in the refractory material. I haven't mentioned that's still a crucial part. In the oven, one thing I haven't mentioned yet is the reason I actually like doing glass more than metal is because you don't need any carbon at all. Glass is already oxidized, so you don't have to protect the part from oxidation like you do with metals. And you can do the whole thing overnight in one cycle. There's no debound and then sintering cycle. You can do the whole thing in one go. So it's even easier than with metal. There's the setup. And I'm using vacuum suction just to make it a little bit easier.
And yeah, it's quite a bit of effort to get one shot.
You can listen to my assistant Sam talking.
Let's do it again.
Why don't you just drink the stuff in the top and mix it in your mouth?
No, that doesn't count.
And just mix it in your mouth.
Just mix it in your mouth. All right, we got our coffee. Here I am drinking it.
Science coffee.
And it wasn't that bad. It was pretty good, honestly. So, yeah, so you can use this to make a coffee filter. It wasn't a very efficient coffee filter by any means, but it absolutely is possible. All right. So let's just talk about now. Finally, I'll show you some more pictures of what we did. One problem was that the refractory material, this aluminum oxide, if you take a look at this, even though the part I showed you before, this one, the inside is kind of these round pieces of glass, like the original Pyrex beads. Even though there's round pieces of glass, if you actually look at the surface of it, take a look, it looks like shards. It's sharp. All right, so it's not actually on the surface. You can feel it. It's very rough, and it's not that smooth glass. This is actually the aluminum oxide binding and fusing to the glass. So aluminum oxide and silicon dioxide, all of these things, they can fuse together at very high temperatures, and you get this rough surface, and that's causing, I think, a little bit of the white color is the aluminum oxide getting stuck. And so I had the idea that what I could do is I could actually print, instead of in aluminum oxide, I could print in some kind of high temperature melting salt, with the idea being that if I printed in the salt, then if it got stuck to it, I could wash it off. And this actually worked. This worked partially, not fully, but what I used was magnesium sulfate. And so magnesium sulfate, high temperature melting salt, related to calcium sulfate, used in casting or plaster. And one problem was this was originally fluffy when I put my parts in here, and then it kind of shrank, and it became this plug. And so it became hard, and then I had to kind of like dig it out. But once I dug it out and I washed it, I like boiled it with water to remove any residual magnesium sulfate, which again worked well. I did actually see a pretty stark improvement between when you use magnesium sulfate and when you use magnesium sulfate when you use aluminum oxide. So on the left we have the aluminum oxide, so it's very sharp. And on the right, we have the magnesium sulfate. It was fluffier and cleaner. And if you look at it under a microscope, it looks more like the original glass. One problem is that this doesn't work at high temperatures. So when I started doing high temperature stuff, it started doing some kind of strange reaction with the magnesium, and I wasn't able to. It started like turning like potato chips, started becoming like fluffy and puffed up. So that wasn't ideal. All right. So I'm still using the aluminum oxide. And a couple more experiments was I tried, instead of using aluminum oxide, I tried putting the parts directly on top. So here are a couple of green parts. And then when I took them out, they were lumpy and misshapen and they cracked. So they were kind of more glassy than before at a very high temperature, but I think you really need that aluminum oxide around it to hold the structure better and provide some support. All right, and let's see. Here's a comparison of copper versus glass printed. This is at probably like 900 or 1000 Celsius. And then finally, my most recent attempt was this bowl that I showed you before, this one. So this is the green bowl printed in vase mode. And then I sintered this at 1300 Celsius. So that's kind of the highest I've been going. And it looks qualitatively quite different than the lower temperature sintered parts. This one, it looks, in person, it looks a little bit more melted. So it looks kind of shinier, not just sparklier, but shinier. And it absolutely sounds incredible. It sounds so much like glass. So I think we should have a video here. Here, sintered bowl making sounds. Oh no, that's the wrong video. That's the bowl rotating. Here, I'm gonna pause real quick. All right, and there we have the glass sounds. So glass sounds. Not bad. So this is glass. It looks like glass. It feels like glass. It's not transparent quite yet. I think we can get it there though. And I think this will be the last video. Is this demo where we have the glass boiling water. So it does hold water. It bleeds a little bit. It does still have some residual porosity, but it holds water long enough to demonstrate that you can boil water in it. I'll bet it's very high temperature resistant. I don't want to hit it with a torch just yet because I'd like to have a couple of standard pieces before I demonstrate that. But yeah, there we have it. So this is kind of an experimental roll. You might have noticed these like little splotches on the parts. That's because it was contaminated a little bit with iron. I've heard that this problem has been fixed. So if you want to try this yourself, it's actually probably one of the easier materials to work with. You don't need as many consumables, and it's not as high temperature as like copper if you just want to have it, be porous. So I absolutely recommend you try using this material. Let me know. I do still have some left, so let me know if you want me to try making something else just to demonstrate, what you can do with it, like a chain or like a whistle or something functional. So with that, thank you for watching. This has been a very long video. I don't really honestly like how this turned out. It's too long. But yeah, let me know if you have any improvements, like, comment, subscribe, find me on MySpace, blah, 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 blah. And I'll see you next time.